Okay, so continuing where we left off, I have 5 more examples here to kind of get you acclimated to verifying trig identities. So let's take a look at number 6. Clearly, the left side of the equation looks more complicated, so I'm going to stick with the left side throughout the whole process. And, one of the strategies I taught you or mentioned is to convert everything to sine and cosine. So I'm going to do that. So cotan we know is cosine over sine. And tangent is sine over cosine. Okay, so at this point, right, you could distribute the sine into here, then you're going to have cosine. Distribute here, then you have sine squared over cosine. But then you're going to get stuck. So instead of distributing the sine right now, I would just add these two fractions. So I showed you in the previous example, right, how to add these two. So multiply by cosine over cosine. For this one right here, multiply by sine over sine. So if I multiply by cosine over cosine, I'm going to get cosine squared theta in the numerator. If I multiply top and bottom by sine over sine, I'm going to get sine squared theta, right? And the denominator, right, is sine theta cosine theta. And so now if you distribute your sine, right, these sine thetas are going to cancel out. And cosine squared plus sine squared theta, we know it's 1. And 1 over cosine, of course, is just secant theta. Okay, so this is an example of, sometimes you might have the right trig identity substituted, but sometimes you might have to perform one step, meaning adding this first and then distributing, as opposed to distributing this first and then trying to combine. So it does make a difference. And again, it's just, verifying trig identities is a little bit of an art. You kind of have to play around with it before you finally get it. All right, so moving on to number 7 here. So in this one, right, both sides look equally the same in terms of complication. You can multiply top and bottom. If you want to manipulate the right-hand side, you can multiply top and bottom by the conjugate of 1 plus cosine alpha. This is alpha, by the way, another letter in the Greek alphabet. But just for kicks, I'm going to manipulate the left-hand side to show you that you can also manipulate by the conjugate, not just of the denominator, which you've learned, right, but also of the numerator. So the conjugate of the numerator is 1 plus cosine alpha. Again, whatever you multiply top by, you multiply bottom by, right? This is just 1, basically. And in my numerator, right, I have a minus b times a plus b, which is a squared minus b squared. So this is 1 minus cosine squared alpha. Erase that, make it a little bit more clear. 1 minus cosine squared alpha. And I have sine alpha times 1 plus cosine alpha. Now notice I did not distribute my sine alpha times 1 plus cosine alpha. Of course, if I distribute, I get sine alpha plus sine alpha cosine alpha, right? And the reason why is because I want to cancel out this sine alpha, right? If I want to cancel out, it makes no sense to distribute it again. And I'm almost done, right? In my numerator, I have a pattern of, in fact, I probably, actually, never mind. I was going to ask, I probably shouldn't have distributed, but this works out. Okay, so 1 minus cosine squared alpha, right? That's just sine squared alpha. Right, and now you can kind of see that these sine alphas are going to cancel out, right? I have a squared over here, I have a, I have a single a. So this cancels out to this, and now I have sine alpha over 1 plus cosine alpha. I probably should have written my equal sign here on the right because I manipulated the left-hand side, so make that correction there. And I'm done. Okay, so this technique really is just showing you can multiply by the conjugate of the numerator. Had you decide to use the right-hand side, you can multiply by the conjugate of the denominator. You'll get the left-hand side. Okay, so remember the solution is not unique. There's more than one correct way of verifying these trig identities. All right, moving on to the last 3 examples. Okay, so on this one right here, right, everything's in terms of sine already. But this one, I can convert everything to sine and cosine. In fact, I'm going to manipulate the left-hand side on this one. So cotan squared is cosine squared x over sine squared x all over 1 plus cosecant. Well, cosecant, that's 1 over sine x. Okay, so it looks like you have a complex fraction, right? I told you complex fractions are not going away. The denominator of this is sine squared x. Denominator of this is sine x. Denominator of this is just 1. So the LCD of top and bottom is just sine squared x. So multiply top and bottom by sine squared x. Okay, so distribute this into this. The sine squares are going to cancel out. You're left with cosine squared x. Sine squared times 1 is sine squared x. Sine squared x times 1 over sine x, you're just left with a single sine x. All right, now this doesn't quite look like this just yet, right? Now notice everything's in terms of sine. So what I need to do with my cosine squared, right, is rewrite it as 1 minus sine squared x. Okay, so again, this is your Pythagorean identity, right? Sine squared plus cosine squared is equal to 1. Hence, cosine squared is equal to 1 minus sine squared. In my denominator, I'm just going to write it out one more time. Okay, so this almost looks like this, right? Somehow I need a 1 minus sine x in the numerator. Why don't you factor this as difference of two squares? Factor out the GCF between these two terms, which is just a single sine x. And now you can see, right, your common factors are going to cancel out. 1 plus sine x and sine x plus 1 are going to cancel out. And now you're left with 1 minus sine x over sine x, which equals the right-hand side over here. Okay, so again, more complex fraction skills. Key step right here after you move on to this line is to substitute cosine squared is equal to 1 minus sine squared x. Okay, so last two examples over here. So number 9 is a problem I've kind of done already, right? You're really just adding these two rational expressions, right? So if I just say, hey, add these two fractions, you would multiply by the missing factor. I'll just show you the work here. 1 minus sine x times 1 plus sine x on top and bottom. And for this guy right here, right, the missing factor is 1 minus sine x. 1 minus sine x. Okay, so this goes back to chapter 6. I told you chapter 6 is the most critical in terms of building your foundation for math 3 and beyond. Okay, so this times this is 1 plus sine x. This times this is 1 minus sine x, right? I would typically ask you to draw parentheses over here, but because they're multiplying by 1, I just, end up with the same term. And in my denominator, right, I have a product of 1 plus sine x times 1 minus sine x. Well, 1 plus sine x times 1 minus sine x, that's 1 minus sine squared x. Again, that's the sum and difference pattern, okay? A plus b times a minus b is a squared minus b squared. Okay, so you kind of really have to know this going from, left to right by foiling, and then going from right to left by factoring, okay? All right, so how does that look like this? Not quite just yet, right? I have to combine like terms over here. Well, the nice thing is my numerator, I just end up with 2, right? These guys cancel out. And 1 minus sine squared x, well, that's just cosine squared x. And 2 over cosine squared x, that's the same thing as 2 secant squared x. Okay, so this one was completed relatively quickly, right? Because I know how to add rational expressions in chapter 6, and now I apply it to trig functions, which is the same concept. Okay, so let me do one last problem here. I'm going to turn to the back. On one of your simplifying trig expressions worksheet, right, I think you had a factor something like this, and now you kind of know where you're going to go to, right? Because I had some students email me, it's like, where do I stop? How do I know when do I stop? Well, you can stop is when you get this expression right here, okay? So I'm going to manipulate the left-hand side. You have to recognize that this is a perfect square, this is a perfect square. And so I'm going to rewrite sine to the fourth x as sine squared x, quantity squared, and cosine to the fourth x as cosine squared x, quantity squared, right? And again, right, I just mentioned that a squared minus b squared is a plus b times a minus b, right? Difference of two squares. So if this is your a term, this is your b term, right? You basically substitute, right? This would be sine squared x plus cosine squared x, right? This is a plus b times a minus b, sine squared x minus cosine squared x. Okay, so factoring, right? Now, sine squared x plus cosine squared x, that's just 1, right? 1 times anything is just itself. So all I have is this term here on the left. So I'll write out that extra line. Make sure you guys write equals over here the whole time. Well, sine squared minus cosine squared, I need to make it look like this, right? And what looks like this is everything's in terms of cosine. So substitute. Sine squared is 1 minus cosine squared x. Okay, so really have to know that Pythagorean identity number 1. And now if you combine like terms, you're going to get 1 minus 2 cosine squared x. Okay, so that's pretty much it in terms of verifying trig identities for this week. If you guys have questions, just email me. If you get stuck on your homework, I can provide you some hints. And, at first, if you don't get it, I would, have a nice eraser on the side and, erase, try a couple times, and then eventually you'll get it.